So, we are discussing the covariant quantization. The Lagrangian density is given by f mu nu, and we have modified this Lagrangian density by adding an additional term which is proportional to del dot a, del mu a mu whole square. This is the Lagrangian density we will consider, and then we will quantize this. Of course, this is not the same as the Maxwell's Lagrangian density, but because of the presence of this additional term, but we will make sure that the additional term does not have any physical effect. Adding this additional term does not have any physical effect. Yeah, so let's so the Fineman Gates in this notation correspond to lambda equal to 1. The although you can consider this for any general lambda, it's we will fix lambda to be a specific value and we will quantize. You can consider lambda to be any arbitrary number and then you can quantize it. Nothing will change. So, yes, according to yesterday's notation, it will be lambda equal to half, which is the guess that we will be working. The equation of motion is given by del alpha a beta del alpha equal to 0. So, let us compute this quantity del L over del alpha a beta. This one will give me a minus f alpha beta, and this one will give me a minus eta alpha beta times lambda times del mu a mu. Now, you know why I have chosen this factor 2 here, because I wanted this to cancel here. That is the reason I am choosing 2. So, the equation of motion is just del alpha of f alpha beta minus lambda eta alpha beta del alpha of del mu a mu equal to 0 plus. So, let us work out what we get. Del alpha a beta minus del beta a alpha plus lambda times del beta del mu a mu equal to 0. This one is nothing but del square acting on a beta minus del beta acting on del alpha a alpha plus lambda del beta acting on del mu a mu equal to 0. Because mu is a dummy index here, I can change it to alpha. Then what I see is the equation of motion is basically del square a beta minus 1 minus lambda times del beta del alpha a alpha equal to 0. This is the equation of motion. You can see that this equation here implies del square acting on del alpha a alpha equal to 0. So, del alpha a alpha acts like a free field. By a suitable boundary condition, by choosing suitable boundary condition, you can set del alpha a alpha to be 0 classically, which is equivalent to Lorentz gauge. So, if you choose this Lorentz gauge that del alpha a alpha equal to 0, throughout the space time, then this is equivalent to saying that you actually restrict yourself to the Maxwell's Lagrangian, but this is all classically. Quantum mechanically, it is not so straightforward. We will see why. This equation here simply implies that the conjugate momentum to the field A beta, which I will denote by pi beta, is given by minus f 0 beta minus eta 0 beta times del mu A mu with a factor of lambda. All right. So, this is the conjugate momentum to the field A beta. You see that pi 0 especially is no longer 0. So, as such you do not have any difficulty in considering the equal time commutation relations, which are given by A mu of x t pi nu of y t is basically I delta mu nu delta of x minus y. So, as an operator equation you can consider this equal time commutation relation, but you can see that pi 0 from this equation is basically f 0 0 is 0. So, pi 0 is simply minus lambda times del mu A mu. So, you cannot set del mu A mu equal to 0 as an operator equation. Quantum mechanically it will be inconsistent to just set this to be 0, because if you set this to 0, then in the equal time commutation relation you will have, for some of these terms you will have the left hand side 0, but the right hand side is not 0. So, this is going to pose a problem that we will see how to solve this. So therefore, as an operator equation we cannot impose the condition that del mu A mu equal to 0. So, we will see how actually we will what is the physical condition that we have to impose, so that we restrict ourselves to the Maxwell's theory. That is what we will discuss in a moment. But before that we will just carry on with what all we have learned so far, and then we will start quantizing. So, the equation of motion is del square A beta minus 1 minus lambda del alpha A alpha equal to 0. As I said, this, although we can consider this lambda to be any arbitrary parameter, it will simplify much if we choose this parameter lambda to be 1, because for when we restrict ourselves to the choice lambda equal to 1, then the equation of motion becomes del square A beta equal to 0, and we know how to handle this equation. So, we will solve this equation. This restriction of this parameter lambda equal to 1 is known as the Fineman Gates. Okay. So, we work in Fineman Gates, for which the equation of motion is simply del square acting on A beta equal to 0. So, this almost looks like again the Klein-Gordon massless Klein-Gordon equation for each of these fields A beta. So, we know how to solve this equation exactly. There will be 4 linearly independent solutions now, because we are no longer doing any kind of gauge fixing here. Therefore, your A beta will go like some epsilon beta of k e to the power minus I k dot x. All right. So let's parameterize this 4 linearly independent polarization to be epsilon lambda mu of k. Lambda varies from 0, 1, 2, 3. Just like in the previous case, when we had performed the gauge fixing, we had 2 linearly independent polarizations. We had 2 transverse polarizations, and those we denoted by epsilon r of k with r equal to 1 and 2. Here there will be 4 linearly independent polarizations. 2 of them are transverse polarizations. The remaining 2 are known as the longitudinal polarization as well as the scalar polarization. So, epsilon 0 mu of k is known as the scalar polarization, and epsilon 3 mu of k is the longitudinal polarization. The most general solution for the field A can be written as a mu of x t is, again in terms of the Fourier components, you will have sum over lambda which varies from 0 to 3 and integration over dqk over 2 pi cube to k 0 times epsilon lambda mu of k a lambda k e to the power minus I k dot x plus epsilon lambda star mu of k a lambda dagger of k e to the power I k dot x. Here k 0 in this integration is given by mod k because this is a massless field. This is the most general solution. Now we are considering this A mu to be a quantum field, therefore these are operators. Now we can look at the canonical commutation relations and then we can see what do they mean in terms of these operators A and A dagger. So what in this case lambda equal to 1, the conjugate momentum pi beta is given by minus f0 beta minus eta 0 beta del mu a mu. You can see that this implies a dot mu of x t a nu of y t, the commutator of a dot and a is given by I eta mu nu delta of x minus y, whereas a dot mu of x t a nu of y t a nu dot of y t is equal to 0. Similarly, a mu of x t a nu of y t equal to 0. So, this is the set of equal time commutation relations. We can substitute this here, and then we can see what we get for the creation for the operators A and A dagger. Before to do that, we will make a choice for the polarizations. First of all, we will assume that the epsilons are real. Okay. So, epsilon mu lambda of k is real, and we will choose these polarizations such that, suppose n hat is a unit vector along the time direction. Okay. Then we will make our choice such that epsilon 0 mu is equal to n hat mu, all right, and then we will choose epsilon 3 mu of k to be the vector which lies in the tk x0 k plane or in the n mu hat k mu. This spans a plane, and this is one linearly independent vector in this plane spanned by n hat and k mu. You choose epsilon 3 to be the unit vector which is orthogonal to n hat mu and which lies in this plane. So, that is the choice for epsilon 3. Epsilon 1 and epsilon 2 are two linearly independent vectors which are orthogonal to each other and which are orthogonal to this plane. Okay. Or I mean, let us say your time is along x0 direction, and let us assume that k is along x3 direction. Then these four linearly independent vectors are simply epsilon 0 is equal to 1 0 0 0, epsilon 1 is 0 1 0 0, epsilon 2 to be 0 0 1 0, and epsilon 3 to be 0 0 0 1. Yeah, unit vector along the, yeah. I mean, not exactly k mu, but you just look at, I mean, you can, this is just one choice that I have given. You need not restrict yourself to four linearly independent. In general, they will satisfy this equation that is given by sum over lambda epsilon lambda mu of k epsilon lambda nu of k star. You do not even have to choose them to be real, and epsilon alpha lambda k epsilon beta lambda k eta alpha beta. This is eta mu nu, and epsilon lambda mu epsilon lambda prime nu eta mu nu is eta lambda lambda prime with a star. Yeah, thank you. All right. So with this choice for the polarizations, we can look at the equal time commutation relations. You can simply substitute the mode expansions in these equations, and then you can show the, I mean, this is almost identical to the free scalar field case, except for the presence of these vectors here, the polarization vectors. Now we are making this particular choice for the polarizations, and then you can substitute them and you can show that the operators A and A dagger satisfy the following relation: A lambda of k, A lambda prime dagger of k prime is given by minus 2 pi cube 2 k 0 eta lambda lambda prime delta of k minus k prime, whereas A lambda k, A lambda prime k prime equal to 0, and so is A lambda dagger of k, A lambda prime dagger of k prime. This is what we get for the commutation relations for the A's and A daggers. So you can again interpret these A's to be the annihilation operators, A daggers to be the creation operators. You can define the vacuum to be the one which is annihilated by A lambda k for lambda equal to 0, 1, 2, 3, and for all k. Then the one particle states, two particle states, etc. will be obtained from the vacuum by acting the creation operators on it. So you might think that okay, everything is perfectly all right. You have now the whole spectrum, and then you can consider the Hamiltonian, and then what are the energy eigenvalues and so on. But it's not so simple. The reason is the following: you look at the one particle states which correspond to the, let us say, scalar polarization. Okay. So there is, so the Fock space of one particle states are usually of this form, that you just consider dqk over 2 pi cube to k 0, some distribution in the momentum space f of k, A lambda dagger of k acting on the vacuum. So a typical one particle state which has a finite spread in the momentum space looks like this. You consider such a state for the scalar polarization. So you just set A lambda equal to, so you just consider the case when lambda equal to 0, and then look at the norm for this one particle state. So what do you get for the norm of this one particle state? So this will be dq k prime over 2 pi cube to k 0 prime, and then you have f star of k prime f of k, then a lambda. I am considering the one particle state corresponding to the scalar polarization. So, a lambda acting on k prime a 0 dagger k. This is what is the norm for the one particle state. Now, I can use this commutation relation to flip this a and a dagger here, but when I do that, what I get is the following. So, a 0 k prime a 0 dagger of k is basically the commutator of a 0 k prime a 0 dagger of k and plus a 0 dagger of k a 0 of k prime. All right. So, now I will substitute this in the expression for the norm of this one particle state corresponding to the scalar polarization. When I substitute that, the contribution from this term vanishes, because I am considering this inside this. So, therefore, you have a vacuum here and there is a ground state acting, and this is an annihilation operator. It will just, when acting on the ground state, it will give you a 0. So, this term vanishes. Therefore, what we get for the norm here is dq k over 2 pi q to k 0 d cube k prime over 2 pi cube to k 0 prime, and this the commutator here. But what is the commutator? If you look at the commutator, it is minus 2 pi cube to k 0 eta lambda lambda prime. So, for lambda equal to 0 and lambda prime equal to 0, it will give you minus 2 pi cube to k 0. Because of this minus sign here, you have a minus 2 pi cube to k 0 times delta k minus k prime. This is all you get. Eta 0 0 is 1, therefore, this is what we have. Now, you can perform the k prime integration, and then there is f of k f star of k prime. If you perform the k prime integration, what you get is norm of the ground state, and there is a minus sign, integration d cube k over 2 pi cube to k 0 mod f of k square. So, what you saw here is that the norm of these one particle states are negative. So, therefore, when you quantize, when you consider this theory and then you quantize it, you see that there are negative norm states present in the Hilbert space. So, therefore, this is of course a problem. You need to get rid of all these negative norm states. So you need to consider how to impose a physical condition which will remove all the negative norm states from the Hilbert space. Remember, we had avoided one of the issues earlier, which was the condition, setting the condition del mu a mu equal to 0. If we set this as an operator equation, then we run into inconsistency in the sense that the canonical commutation relations that we have adopted cannot be satisfied if we consider this as an operator equation. Left hand side becomes 0, whereas right hand side is non-zero, and so on. So we need to worry how to impose this condition also in order to recover the Maxwell's theory. What we will say is that we will say the states in the Hilbert space are physical if they satisfy this condition that suppose psi is a state for which del mu a mu, the expectation value of this operator in this state is 0, then this is a physical state. So this is the physical state condition that we are going to impose. Although we cannot set del mu a mu equal to 0 as an operator equation, we can consider the expectation value of this operator in any arbitrary state, and then we will require that this expectation value is always 0. Yeah. So we are saying that a state is a physical state if it satisfies this condition that expectation value of del mu a mu equal to 0. Otherwise, it is not a physical state. And then we will see what is the implication of this physical state condition. We will see that this physical state condition not only will give us the Maxwell's theory, it will also remove all the unwanted negative norm states that appear in the spectrum here. So the physical Hilbert space will not contain any of these negative norm states. That is what we will see in a moment. So this condition here is equivalent to imposing this, that del mu a mu plus acting on the state psi equal to 0. You can see that this especially implies this one. So let us look at this condition here. A mu plus contains the positive frequency part of the mode expansion. Therefore, a mu plus of x according to our definition is dqk over 2 pi q to k0 sum over lambda equal to 0 to 3 epsilon lambda mu of k a lambda of k e to the power minus I k dot x. So what do we get when we impose this condition here? When we impose the condition that this quantity acting on some state gives you 0. So to do that, let's consider a basis in the Hilbert space which is given by this formula. A basis of states is I can choose a basis of states which are of this form psi t phi. Do you understand what is this? Psi t correspond to the states which arise due to the transverse polarizations, whereas this phi here correspond to the longitudinal and scalar polarization. So this is a scalar or this corresponds to transverse polarization. So, this now what we get is, we will see what happens when mu plus acts on a state like this. Because this is this corresponds to the scalar polarization, therefore this state phi here will be of this form. It will be obtained by A0 K1 A0 dagger K1 A0 dagger K2. There will be a number of A0 dagger operators, and then there will be a number of A3 dagger K1 prime, A3 dagger of Kn prime, etc., acting on the ground state here. So, a general n particle state corresponding to this will have n such operators here, whereas this psi t here is just given by, again this state psi t will be of this form, where you have transverse polarizations A1 dagger of K1 and A1 dagger of Kr, number of such operators, and then you will have also A2 dagger of K1, A dagger of Kn acting on the ground state here. Now, what happens is that now what we will see what mu plus of x acting on this state psi transpose and phi equal to 0 gives us. Okay. Thank you. This is, there is this del mu mu acting on this. So, what do we get from here? As you can see, this d cube k over 2 pi cube 2 k 0, and this derivative acting on this will give me sum over lambda equal to 0 to 3 k mu epsilon mu lambda of k with a minus I a lambda of k e to the power minus I k dot x phi equal to 0. Okay. Now, because of this appearance of this k mu here, the transverse polarizations will simply go away, right? Because for lambda equal to 1 and 2, this is simply 0, although lambda is summed over all the values, lambda equal to 1 and 2 correspond to the transverse polarization. So, this simply kills the lambda equal to 1 and 2. Therefore, what is left here is d cube k over 2 pi cube 2 k 0, and there is a minus I, and then a 0 of k minus a 3 of k times e to the power minus I k dot x. Is this clear? This lambda equal to 1 and 2 just goes away, and k dot epsilon just gives you this minus sign here. K is just a null vector, and k you can choose to be something like 1 0 0 1, and then this will simply imply, if according to our choice, epsilon 0 is just 1 0 0 0, whereas epsilon 3 0 0 0 1, and then this factor will simply give you this. Because this involves only the scalar and longitudinal polarization, it is irrelevant to consider this transverse part here. So, this simply implies that a 0 k minus a 3 k acting on some n particle state gives you 0. Okay. So, this is what is equivalent to imposing this condition del mu a mu plus on this state psi equal to 0. Let us say consider the number operator corresponding to the scalar and longitudinal polarization. You can work out the expression for the number operator. You can show that the number operator is simply dq over 2 pi q 2 k 0 a 0 k a 0 dagger minus a 3, I think there is a 3 here, there is a 3 here, minus a 0 k a 0 dagger of k a 0 . This is the number operator corresponding to the longitudinal and scalar polarization. You can look at some n particle state phi n, okay, any arbitrary state phi here can be expressed as some coefficient C n times phi n summed over n, where phi n here is an n particle state corresponding to the scalar and longitudinal polarization. So, there will be a 0 daggers and a 3 daggers, and there will be n such objects acting on the vacuum. That is what I am denoting by phi n, and a phi in general is summed over all these things. So, now if you look at this quantity here, you can show that this to k0 and a3 dagger k a3 of k minus a0 dagger k a0 k phi n here. But now this phi n satisfies this condition that a0 acting on phi n is equal to a3 acting on phi n. So, I can use that relation. When I use that, this will become phi n d cube k over 2 pi cube to k0 and this is a3 dagger k minus a 0 dagger of k a0 of k acting on phi n, right. Suppose phi n is not equal to phi 0, suppose phi n, of course in general it will have C0 times ground state plus C1 times 1 particle state and so on, okay. Or in general phi n will have something. So suppose n is not 0, okay. If n is not 0, then this is not ground state. So in that case, what you can see is that this quantity here is simply equal to 0, because you can consider this acting on this. This is simply, this is always equal to 0. This quantity here is always equal to 0, and this is because if n is ground state, then it's of course it annihilates the ground state. Even if n is not equal to ground state, you can consider this, and then this, when it acts on this one from the right, again you can use the conjugate of this equation here, and this conjugate shows that this is equal to 0, okay. So what does it mean? It simply means that if n is the number operator, then n acting on phi n is just n times phi n, right. But this calculation shows that this is equal to 0. So therefore phi n, which is n times phi n which is equal to 0, basically implies that phi n equal to 0 when n is not equal to 0, or in other words, if n equal to 0, this is just the ground state which is unit norm, therefore this quantity is delta n 0. Therefore, if you consider an arbitrary state corresponding to the scalar and longitudinal polarization which satisfy this condition here, then this state can either be ground state or it will have a 0 null, okay. So these are all null states except for the ground state. All the n particle states corresponding to the scalar and longitudinal polarization which satisfy the physical state condition are all null states. And then you can see that if you consider any physical observable, and then if you compute the expectation value, for example, let us say you consider the Hamiltonian of the theory, and then you compute the expectation value of the Hamiltonian in the physical Hilbert space, then these states, these null states completely decouple, they just drop out from the expectation values. That is what you can see when you do an explicit computation. So although these states are there, they do not contribute to any physical measurable quantities. We have said the physical Hilbert space is spanned by states of this type, psi equal to psi t times phi. These involves the transverse polarizations, whereas these involves the scalar polarization. However, not all the states in the full Hilbert space satisfy the physical state condition, which is given by del dot A plus acting on psi is equal to 0. For example, we have considered the state, the one particle state, which is given by 1 is equal to integration dq k over 2 pi q 2 omega f of k times a 0 dagger k acting on the vacuum, and then we have seen that this state has negative norm. The norm of the state is less than 0. So, this state, for example, does not satisfy the physical state condition del dot A plus acting on psi equal to 0. Any state of this type, which is psi t, if you consider any state of this type, which is actually given by the creation, which is actually generated by acting creation operators for the transverse polarizations, which is a dagger 2 k, so on a dagger 1 k prime and so on like this. So, states of these type do satisfy the physical state condition. So, they are there in the physical Hilbert space. There are other states, for example, states like this, they do not satisfy the physical state condition. So, they do not belong to the physical Hilbert space. However, in addition to these states, there are a bunch of states which are also generated by the scalar as well as so which are of this type a 0 dagger k acting on this, or a 3 dagger k acting on this, or a bunch of operators like a 0 dagger k, a 3 dagger k, so on acting on the state. So, phi 0 I will call them phi n, these are the n particle states which have 0 norms. So, phi n norm of these states are 0. There are a bunch of states which are generated by acting these operators on the vacuum with 0 norm. These will be there in the physical Hilbert space. However, because these states have 0 norm, therefore, you consider any observable quantity, expectation values of any operator, these states do not contribute at all. It is only these states which are generated by acting the transverse and by acting the creation operators corresponding to the transverse polarizations, they only generate the physical Hilbert space.